In this video, we're going to be proving this combinatorial identity using a Pascal's triangle argument. The Pascal's triangle is shown here above, and by using algebra and factorials. So the identity we're going to prove here today is a very basic one in combinatorics here. So it basically states that n choose r is going to be equal to n choose n minus r. So this is something that you're going to use pretty much every time in a problem. So when dealing with combinations. So for example, 4 choose 2 would be equal to 4 choose 4 minus 2, which is also 4 choose 2. A better example might be 4 choose 1, which would be equal to 4 choose 3, because 4 minus 1 is 3, and that's going to be your lower number in the choose there. Okay, so what we want to do here is prove this identity first using a Pascal's triangle argument. So what this means is we're going to show that this identity is true using this triangle up here. And Pascal's triangle is basically just a series of rows with increasing numbers of entries in each row, and all of them can be related to combinations. Each entry is a combination here, an n choose r number. And it just so happens that all of these entries here, the value of each entry is the same as the number of paths from the very topmost entry, which is this, to that entry. So we're going to go ahead and use that fact to prove this identity. So down here we have n choose n minus r. So that, this right here, is going to give you some entry on the triangle. Depending on what your n and r is, could be any entry. But no matter what it is, it's going to be the result of n choose n minus r is going to give you a value that, like we said earlier, is the number of paths from the top to n choose n minus r. And so really what we have to do here to visualize the pattern, the relationship between these two n choose r numbers, is to test some example values. So once we get some specific values, then we can then make some generalizations on those. So let's, for example, set n equal to 5 and r equal to 3. So our left side becomes 5 choose 3, and our right side is equal to 5 choose n minus r, so 5 choose 2. So if you look back up at our triangle here, you can see we have 5 choose 2 and 5 choose 3. They're right next to each other. You'll also note that 5 choose 3 is 2 entries from the edge of the row here. The edge, the last n choose r number in the row is 5 choose 5. And the first one is 5 choose 0. And 5 choose 3 is 2 entries from the 5 choose 5. And so is 5 choose 2 from the first entry. So they're mirrors of each other, or they're symmetrical, you could say. And if you really wanted to make sure of this, you could try one more example. Let's say n equals 4 and r equals 1. So you'd have 4 choose 1 is equal to 4 choose 4 minus 1, which, or 4 choose 4 minus, yeah, so what it's going to be is essentially we have 4 choose 1 and 4, so it's going to be 4 choose 3. So as you can see on the triangle, 4 choose 1 and 4 choose 3 appear here. And again, they're the same distance from the edge of the rows, one entry. And they're again symmetrical or mirrored. And this will keep happening no matter what your values are for n and r. So this means that since they're basically the same entry as far as the triangle is concerned, because they're symmetric, they're the same distance from the edge, it doesn't matter which side of on either side of the middle row that you're on, if it's on the farther to the left, farther to the right, it's going to be the same number of paths from the top to that entry. And since it's always going to be like that for any for any values for n and r, that's why this identity is true, because these are always going to be mirrors of each other in each row of the triangle. Okay, so that was proving the identity using a Pascal's triangle argument. So now we're going to use algebra, which might be a little bit clearer and more concrete than this kind of Pascal's triangle stuff here. So, using algebra, we're going to want to use the principle here. It's going to be very important. I'm going to write it off to the side here. That any n choose r number can be expressed as n factorial over r factorial times n minus r factorial. So that's just the way any n choose r number can be expressed, is in this form. So that's going to be very useful here. Basically, what we're going to try to do is express both sides of this identity, this equation, using factorials, and if they're both equal, as we can see using factorials, then it definitely means they're true. Okay, so we're going to start writing this out. We already know that n choose r equal to n factorial over r factorial times n minus r factorial. So we can just write that here, because that's literally what we have in the identity. And that's going to be equal to n choose n minus r. So that one's a little bit more complex. We still have the n on top only. So it's just going to be n factorial. And that's going to be over n minus r factorial. Because if our r factorial, the r is n minus r in this case. And that's going to be times n minus r factorial. Or n minus r, and then the whole thing is factorial. So, and this is because in the original equation for this, the original definition for n choose r, it's n minus r factorial. And in this case, n is just this n up here. So the n and the r, this entire r is n minus r. So that's where that comes from. It's going to be the n minus r. N minus r over here, and then n minus r over here, then the whole thing factorial. So we have this equation now that we can then begin to simplify to see if it's really going to be equal on both sides. So on the left side, we're pretty much simplified down as far as we can go. We can't go any further. No more like terms to combine, or we don't need to. Now on the right side, though, we can do some simplification here. So we have this n minus r factorial. It's still going to be n factorial on top, because that's the only thing over there. And so what we're going to wind up with is just n minus r factorial times r factorial. And you can see up here, it's really this second pair of parentheses here that we're simplifying, because we have this n minus n, that cancels out the n's, and you're left with the r, so it becomes just r factorial, and of course that multiplied by n minus r factorial. So, as you can see here, these two sides of the equation are exactly the same. They're exactly the same because one's just in a different order, that's all. We have r factorial times n minus r factorial, and we have n minus r factorial times r factorial. It's the same exact thing, commutative property of multiplication. It's the same thing, it's just in a different order. So, we successfully proved this identity using algebra because we got to the same result on both sides of the equation. Two ways of counting the same thing, essentially. Same kind of thing with the Pascal's triangle, two ways of getting to the same number of paths, mirrored on opposite sides of the row. Okay, and we successfully used those two methods to prove the identity n choose r equals n choose n minus r.